In the last video, we had an introduction to 3D coordinate systems. We looked at the XYZ coordinate axes and we talked about the right-hand rule to help us keep track of the labeling. Remember, this picture is a little bit rotated, so we want to spin it 90 degrees in this direction so that the forefinger corresponds to the x-axis in the positive direction. The other three fingers correspond to the y-axis in the positive direction, and then the thumb is the z-axis. So right-hand rule helps us to keep track of the labels for the 3D coordinate system. We use GeoGebra to plot three-dimensional objects. This is a fantastic resource that I highly encourage you to take advantage of. It's totally free, and it's really helpful for understanding the concepts. We talked about some terminology here. R3 is the name that we use for three-dimensional space. Three-dimensional space consists of all triples, x, y, z, where x, y, and z are any real numbers. When we plot three-dimensional equations using x, y, and z, we have surfaces. So we talked about different surfaces such as planes. We talked about how to get the equation for a sphere. And then plotting points, we just plot a triple. The way to find distances in 3 dimensions is to use a generalization of the distance formula for 2 dimensions, which really comes from the Pythagorean theorem, as we saw here. Let's work through some examples now to help us understand these concepts better. In example 1, we're given the equation of a plane, and we want to know which of these points are on that plane. If we were to graph this plane, which of these points are on it? So to figure this out, we need to plug the coordinates of the points in for x, y, and z and see if the output is 4. Let's do that with the point 0, 0, 0. If we plug in 0, 0, 0 into this equation of the plane, then we'd have 2 times 0 minus 3 times 0 plus 0. That all equals 0, which is not 4. So this point does not lie on the plane because it does not satisfy the equation. Let's try the point 2, 0, 0. We're going to plug in 2 for x and 0 for y and z. So 2 times x, which is 2, minus 3 times 0, plus 0. Well, 2 times 2 is 4, minus 0 plus 0. We get 4, which is what we're supposed to get. So this point does lie on the plane. It works. How about the point 3, 2, 1? So we have 2 times 3 minus 3 times 2 plus 1, plugging in 3, 2, and 1 for the point. And 2 times 3, 6, minus another 6 plus 1, we just get 1 here. That's not equal to 4, so this point does not work. Let's try the point 3, 1, 1. 2 times 3 minus 3 times 1 plus 1. 2 times 3 is 6. Subtract 3 and we have 3. Add 1, that's 4. Yes, this point works. We get 4 again. So this point and this point both lie on the plane. Let's quickly visualize this in GeoGebra. Here's the plane with the equation 2x minus 3y plus z equals 4. That's what that plane looks like, extending infinitely in all directions. Now let's look at the different points. We had the point 0, 0, 0, and we discovered that that does not lie on the plane. So you can see there that point is not on the plane. 2, 0, 0 is on the plane. So there's that point 2, 0, 0. That's on the surface of the plane. 3, 2, 1, that was not on the plane. That one's off. But then finally 3, 1, 1, that one is on the plane. So we can see there 2 of the points are on the plane. The other 2 are not. To figure out if a point's on the plane, we just plug the x, y, z values of the point into the equation for the plane and see if equality is satisfied. Moving on to example 2, we want to find the equation of the sphere centered at 1, negative 1, 0 with a radius of 5. So the general formula for a sphere is x minus the x value of the center squared plus y minus the y value of the center squared plus z minus the z value squared equals the radius squared. A, B, and C are the components or the coordinates of the center of the sphere. So our A, B, and C are 1, negative 1, 0. So writing this equation down, we have x minus 1 squared plus y minus negative 1, so y plus 1 squared. And we don't drop the z term, we just have z minus 0 squared. So z minus 0 squared is just z squared. This equals the radius squared. We have a radius of 5, so this all equals 25. Here is the equation of the sphere, centered at 1, negative 1, 0, with a radius of 5. Let's practice using the distance formula with example 3. We have 2 points. We want to find the distance between them. So from the previous page, the distance formula is the square root of the x components difference, x2 minus x1 squared, plus y2 minus y1 squared, plus z2 minus z1 squared. Now, if you'll notice when we wrote the little proof here, I actually switched up the order. Instead of having x1 minus x2, I had x2 minus x1. That does not matter at all. Because we're squaring The only difference between x1 minus x2 and x2 minus x1 will be a plus or minus sign. But since we're squaring, that doesn't matter. You can do either order here between any of the points. It really doesn't matter. You just take the difference of the points in either order, and since you're squaring, it doesn't matter which order you do. So back to our example, we can take the difference of these points in any order we want. I like to be consistent, just 5 minus -1, 3 minus 0, 1 minus 3, and we'll just plug those into the formula. So we have the square root. 5 minus -1 would be 5 plus 1. That's the difference of the x components. And then difference of the y, we have 3 minus 0 squared. Difference of the z, 1 minus 3 squared. Well, 5 plus 1 is 6. 6 squared is 36, so we'll have 36. 3 minus 0, 3. 3 squared is 9. And then 1 minus 3 is -2, but since we're squaring, -2 squared is 4. So we have 36 plus 9 plus 4. That equals 49, and since we're taking the square root of 49 is 7. So the distance between these 2 points in 3 dimensions is 7 by using the distance formula. Now take a look at example 4. Example 4 is going to be related to what we just did. We want to find the equation of the sphere with a center at -1, 0, 3. That's a point that we worked with in the last example. And we know that the point 5, 3, 1 lies on the surface of the sphere. Well, how do we get an equation of a sphere that satisfies this? We don't have a radius here, or do we? We found the radius in the previous problem. The distance between these 2 points is 7. That's the radius of the sphere. Since we have a center and a radius, we can write down the formula just like we did for example 2. So let's write this down. We have x minus -1, that'd be x plus 1 squared, plus y minus 0 squared, plus z minus 3 squared. That equals the radius squared. Radius is 7, so that equals 49. Once again, I'm using -1 for the a value here, and then y minus 0 squared, z minus 3 squared. That all equals the radius squared. And we know that the radius of the sphere must be 7 because the distance between the center and a point that's on the surface of the sphere, that distance is 7. Let's visualize this in GeoGebra. Let's go ahead and put the center of the point in first. The center's at -1, 0, 3. So in the x direction, that's the red axis, we go -1 in the red direction, 0 in the y direction. So along the green axis, which is the y axis, we don't move anywhere. Then up 3 in the z direction. So vertically, we've gone a distance of 3. There's the center of the sphere. And a point that's on the surface of the sphere is 5, 3, 1, which is right there. This sphere that we found with the equation x plus 1 squared plus y squared plus z minus 3 squared equals 49, this will have the center at point A and pass through point B. There it is. Isn't that cool? We just found that equation by first finding the distance between the 2 points, and we knew that that would be the radius of our sphere, and then using the formula for a sphere in 3 dimensions, we were able to find exactly what this sphere is. Example 5 is related to the problem that we just solved. We want to know which of these points are in the interior of the sphere whose equation we just found. How do we answer this question? How do we figure out if these points are actually inside this 3-dimensional sphere? Well, the sphere consists of all the points that are a distance of 7 away from the point -1, 0, 3. We have the shell of the sphere. That's a distance of 7 everywhere from -1, 0, 3. So for these points to be in the interior of the sphere, they have to be a distance of less than 7 from the center, from the point -1, 0, 3. So as we solve this problem, we're trying to figure out if the distance from each of these points to the center of the sphere is less than 7. Let's write that down. For the points to be on the interior of the sphere, we need the distance from the point -1, 0, 3 to be less than 7. Take a look at point A. Is this point a distance of less than 7? Well, the only difference between that point and the center is the z component. Instead of having a 3, we have a 4. So what's the distance between the center and this point? Well, we've only moved 1 up in the z direction. So the distance here is 1. So that's a distance of less than 7. Therefore, the point -1, 0, 4 must be on the interior of the sphere. How about the origin, 0, 0, 0? Is that on the interior of the sphere? Well, here we have to really set up the distance formula. We'll do this kind of quickly, but we're using the same distance formula that we've used before. For the point 0, 0, 0, I'm just going to take the components of this point, minus 0 everywhere, square that, and then take the square root. I get square root of -1 minus 0 squared is 1 squared, which is 1. And then 0 minus 0 squared, that's 0. 3 minus 0 squared, That's 3 squared. So we have the square root of 1 squared plus 3 squared. 3 squared is 9. Square root of 1 plus 9 square root of 10. Square root of 10 is less than 7. So this point also is on the interior of the sphere. Let's take a look at this point here, and we'll write out some more steps for the distance formula. So for the point C, 5, 4, 1, the distance would be square root of, now we take the difference of the corresponding components. 5 minus negative 1, 4 minus 0, 1 minus 3. So 5 minus negative 1 would be 5 plus 1 squared, plus 4 minus 0 squared, plus 1 minus 3 squared. And what do we get here? Well, 5 plus 1 is 6. 6 squared is 36. 4 minus 0, that's 4. 4 squared, 16. And then 1 minus 3 is negative 2. Negative 2 squared is just positive 4. So we have 36 plus 16 plus 4. If you add those numbers together, you get 56. So we have the square root of 56. Is this larger than 7? Well, yes, it is, because 7 is the square root of 49. We have something larger than 49. Square root of 56 is between 7 and 8. So we have a larger distance than just 7. Therefore, point C is not inside the sphere. Let's look at point D. Here we have the point 3, negative 2, negative 1. We play the same game. We want to find the distance from this point to the center of the sphere and see if that distance is less than 7. So we set up the distance formula once again. Distance equals square root of, let's do this a little bit quicker. 3 minus negative 1, that'd be 3 plus 1 is 4. 4 squared is 16. Negative 2 minus 0 is just negative 2. Negative 2 squared is 4. Negative 1 minus 3 is negative 4. 4 squared, 16. So we have 16 plus 16, that's 32, plus 4, that's 36. Yes, so we have square root of 36, which is 6. That's a distance of less than 7. So this point as well is on the interior of the sphere. So we have 3 points that are inside the sphere, 1 point that is not. Let's look at this in GeoGebra. Here once again is our sphere with a radius of 7 centered at negative 1, 0, 3. Let's take a look at those points that we just considered. We have the point negative 1, 0, 4. That one is in the sphere. There it is. And then the point 0, 0, 0, the origin, that's also in the sphere. Kind of hard to see it in there, but the origin is on the interior of that sphere. And then 5, 4, 1. This one was not in the sphere. So we can see clearly that's outside the sphere. Lastly, 3, negative 2, negative 1, that one's in the sphere as well. There it is. So there we have it. 3 of the points are inside the sphere. 1 of the point is outside of the sphere.